There's a moon smaller than the country of Spain, orbiting a planet 900 million miles from where you are sitting right now, and inside that moon is an ocean scientists believe could be hiding the answer to the biggest question humans have ever asked. Not, is there life out there? That question is old. The new question is sharper, colder, and far more exciting. Does that ocean already have everything it needs to make life happen? And after 2 decades of data, a supercomputer, and a spacecraft that died 9 years ago, the answer keeps landing closer and closer to yes. Saturn itself needs no introduction. Even people who have never picked up a telescope recognize its rings on sight, one of the most photographed objects in the night sky. But Saturn is not traveling alone. It carries more than 140 known moons with it, ranging from house-sized chunk, as of rock to Titan. A moon larger than the planet Mercury, with its own thick atmosphere and lakes of liquid methane. Against a lineup like that, a 300-mile wide ice ball tucked among the rings never stood much chance of getting attention. It took a dedicated spacecraft, sent specifically to study the system up close, to notice that it deserved a second look at all. The moon is called Enceladus. If you have never heard the name, you are not alone, because it spent most of its existence as a footnote next to its far more famous neighbor, Saturn's rings. It is tiny, just over 300 miles across, small enough that you could walk its entire circumference, in about the time it takes to drive across a mid-sized American state. It is covered in ice so bright and so clean that it reflects more than 90% of the sunlight that hits it, giving it roughly the same shine as fresh snow. For most of the 20th century, nobody thought twice about it. It looked like a dead, frozen rock, the kind of object astronomers catalog and then forget. Then, in 2005, a spacecraft called Cassini flew close enough to look, and what it found rewrote the assumptions. Cassini was a joint NASA and European Space Agency mission that arrived at Saturn in 2004 and spent the next 13 years orbiting the planet and its moons. During one of its early passes near Enceladus, its instruments picked up something strange. A magnetometer detected a disturbance in Saturnus, this magnetic field near the moon, almost as if something invisible were pushing back against it. Not long after, cameras caught the real answer. Massive plumes of water vapor and ice crystals erupting from cracks near the moon's south pole, blasting hundreds of miles into space. A tiny, supposedly dead ball of ice was venting geysers like a cosmic fire hydrant. That single observation changed the direction of planetary science, according to Linda Spilker, who served as Cassini's project scientist at NASA's Jet Propulsion Laboratory. Because geysers do not come from nowhere. Something has to feed them, and the only thing that made sense was liquid water hidden under the ice, being forced up through fractures by pressure and heat from below. Before Cassini, nobody had a real reason to expect this. Enceladus orbits Saturn well outside what astronomers call the traditional habitable zone, the narrow band around a star where temperatures allow liquid water to exist on a surface without extra help. Saturn sits roughly 9.5 times farther from the Sun than Earth does, meaning sunlight arriving at Enceladus is only a small fraction as strong as what reaches us. By every old-fashioned rule of thumb, a moon out there should be a frozen, geologically dead rock. And for a long time, that is exactly what scientists assumed it was. The geysers broke that assumption completely because they proved something was generating heat from the inside, independent of the sun entirely, powerful enough to keep liquid water flowing under miles of ice in one of the coldest regions of the solar system. Over the following years, Cassini kept flying past Enceladus, sometimes diving directly through the plumes themselves, sampling the spray with instruments built to catch dust and gas. What it found piece by piece became one of the most compelling stories in modern astronomy. Underneath that icy shell, hell sits a global ocean, salty, liquid, and in contact with a rocky core. Scientists now believe this ocean has existed for a very long time, kept from freezing solid by heat generated as Saturn's gravity squeezes and stretches the moon on every orbit, a process called tidal heating. But an ocean by itself is not exciting. Earth has oceans. Mars might have had oceans once. What makes Enceladus different is what is dissolved inside that water, and this is where the story gets specific, because the details are not speculation. They are measurements. The first major clue came from something called the Cosmic Dust Analyzer, an instrument built by German scientists and flown on Cassini. As the spacecraft passed through the plume, this instrument detected sodium and potassium salts in the spray. That might sound like a small thing, but it was actually a critical piece of evidence, B, because salt does not show up in ice by accident. It shows up when liquid water spends a long time sitting against rock, slowly dissolving minerals out of it. Finding salt in the plume told scientists the ocean beneath Enceladus was not just sitting in a sealed icy shell. It was touching stone, actively interacting with a rocky seafloor, the same kind of chemistry that drives interesting reactions in oceans here on Earth. Then came the discovery of molecular hydrogen, A later Cassini flyby, one specifically designed to sample the plume's gas composition, found hydrogen gas mixed into the spray. On Earth, hydrogen like this usually comes from a very particular kind of geology. Hydrothermal vents, cracks in the ocean floor where hot water reacts with rock and releases hydrogen as a byproduct. Around vents like these on our own planet, entire ecosystems thrive without ever seeing sunlight, powered instead by the chemical energy in that hydrogen. Finding Heidi. Rogan in Enceladus's plume told scientists something remarkable. This moon might have the same kind of underwater hot springs and possibly the same kind of chemical energy source that keeps life running in the darkest parts of our own oceans. To understand why that mattered so much, it helps to look at Earth's own deep ocean. Along the mid-ocean ridges, thousands of feet below the surface, far past any trace of sunlight, seawater seeps down through cracks in the crust, gets heated by magma, and rises back up loaded with dissolved minerals and gas, including hydrogen. Around those vents, scientists have found some of the strangest and most resilient life on the planet. Tube worms, blind shrimp, entire colonies of bacteria that never see a single photon of light and never need to, because they run their whole metabolism on chemical energy instead. That process is called chemosynthesis, and it is how life could survive or even begin on a world with no sunlight at all. Finding hydrogen streaming out of Enceladus's plumes was the first strong signal that the exact same kind of process might be happening at the bottom of an alien ocean, hundreds of millions of miles from Earth. Salt told researchers the ocean touches rock. Hydrogen told them there might be an energy source down there. The third piece of the puzzle arrived a little later and closed a gap that had bothered scientists for years: phosphorus. Every living thing on Earth needs phosphorus. It is a core ingredient in DNA, in RNA, in the membranes of every cell, and in the molecules that store and transfer energy inside living organisms. For a long time, phosphorus was considered the missing piece in the Enceladus story, an element astrobiologists worried might simply be too scarce in that ocean to matter. Then, in a 2023 re-examination of Cassini's archived data, scientists confirmed phosphorus in ice grains ejected from the moon, and not in trace amounts, but at concentrations that suggested it was actually abundant in the ocean below. That discovery filled in one of the last major blanks in the ingredient list for life as we understand it. So, by the middle of this decade, the case looked like this: a salty ocean, evidence it touches rock, a plausible chemical energy source in the form of hydrogen, and now a confirmed abundant supply of phosphorus. 4 separate lines of evidence, gathered years apart, using different instruments, on different flybys, all pointing the same direction. And then, instead of slowing down, the discoveries picked up speed, because scientists realized something important. Cassini's mission might be over, but its data was not finished talking. In December 2023, NASA researchers published a study built entirely on archived Cassini measurements, and it added something new to the list. They found strong confirmation of hydrogen cyanide in the plume, a molecule that sounds alarming, known by name, but is actually considered one of the most important building blocks in the origin of life. Hydrogen cyanide is a starting point for the chemical pathways that can eventually form amino acids, the components that link together to build proteins. The same study also uncovered a wider range of oxidized organic compounds than anyone had previously identified in the plume, suggesting there are more chemical pathways available to fuel biological activity than scientists had assumed. One of the researchers behind the work, a doctoral student named Jonah Peter, said the discovery of hydrogen cyanide was particularly exciting, precisely because it sits at the starting line of so many theories about how life first began. Then in late 2025, another team dug back into the archives, this time focused on ice grains collected extremely close to the moon's surface, just 13 miles up, during one of Cassini's deepest dives through the plume. This mattered because most previous organic analysis had relied on CLIS collected much farther away, inside Saturn's E-ring, where the material has had time to degrade and mix with other debris. Sampling this close to the source was the next best thing to actually reaching into the ocean itself. And what they found was a wider diversity of organic molecules than ever been confirmed in fresh Enceladus material published in the journal Nature Astronomy. The freshness of the sample mattered because it strengthened the case that this organic chemistry is happening actively, right now, inside that ocean, rather than being some leftover relic from billions of years ago. Around the same time, a separate team led by researcher Nozer Khawaja at the Free University of Berlin went back to a Cassini sample collected directly over the South Pole and ran a fresh analysis using updated techniques. Their results confirmed the presence of organic molecules alongside what scientists refer to using the acronym CNOPS, standing for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the 6 elements considered essential to every form of life we know of on Earth. Their analysis confirmed 5 of those 6 directly. with abundant hydrogen and strong support for hydrothermal activity happening at the base of that ocean. Sulfur remains the one element still awaiting direct confirmation, but the other 5, sitting together in one sample, is about as close as this kind of remote chemistry can get to a complete list. Meanwhile, a completely different research group was tackling a different question entirely. Not what is in the ocean, but how stable that ocean actually is. An ocean full of the right chemicals does not mean much if it freezes solid in a few million years. Life, at least as far as we understand it, generally needs a long, stable window of time to get started and to develop. So, researchers led by Georgina Miles, working with the Planetary Science Institute, Oxford University, and the Southwest Research Institute, set out to measure Enceladus's heat budget directly. For years, almost all the attention had gone to the South Pole, since that is where the geysers erupt and where the heat was obviously escaping. But in a study published in July 2026, this team found something nobody had confirmed before. Significant heat flow coming out of the moon's north pole as well, a region that had always looked quiet and unremarkable by comparison. By measuring seasonal temperature shifts at the North Pole and combining that with existing measurements from the highly active south, the team produced the first real observational estimate of Enceladus's total energy loss, calculating it at under 54 gigawatts. That number lines up almost perfectly with the predicted energy input from tidal heating, somewhere between 50 and 55 gigawatts. In plain RMS, the moon is not losing more heat than it is generating. The books balance. And when the books balance, an ocean does not freeze over on any timescale that would matter for the development of life. Miles put it simply, understanding how long that energy supply lasts is central to knowing whether Enceladus can actually support life, not just host the right chemistry for a geological blink of an eye. Just one day earlier, in a related piece of reporting published in July 2026, scientists laid out the full habitability case in the clearest terms yet, built around those same 3 central pillars. Sodium salts confirming ocean rock interaction, molecule, R hydrogen suggesting available chemical energy, and phosphates confirming the presence of a critical life-building element. But that same reporting was careful to include an important caveat, one that any responsible look at this topic has to include. Cassini never entered that ocean. It never detected life. What it did was sample material that had traveled up through cracks in the ice and out into open space, meaning every single conclusion drawn from that data depends on correctly interpreting a sample that made a long, cold journey before anyone ever measured it. The chemistry can OT tell scientists whether life ever actually started down there. It cannot answer questions about the ocean's exact temperature range, its internal circulation, its chemical gradients, or whether any usable energy source exists at a rate and location that a living organism could actually take advantage of. Cassini was built and launched before the plume was even discovered. It was never equipped to make a definitive life detection measurement, and nothing it gathered can close that gap. There is also a quieter, more technical thread running through recent Enceladus research that rarely makes headlines, but matters enormously to scientists trying to understand this moon, figuring out exactly how much material the plumes are actually losing to space. November 2025, a team using supercomputers at the Texas Advanced Computing Center ran a new kind of simulation, one that modeled the physics of the plume gas far more rigorously than earlier techniques allowed. Their results showed that Enceladus's plumes are losing somewhere, between 20 and 40% less mass to space than earlier estimates had suggested. That might sound like a footnote, but it directly affects how scientists model what is happening underground, including the pressure, temperature, and structure of the vents feeding those geysers in the first place. Enceladus is so small and its gravity so weak that it cannot fully hold onto the icy jets erupting from its surface, and getting the T-math right is the difference between an accurate model of the subsurface and a wildly wrong one. Put all of this together, and here is where the science actually stands, without exaggeration and without hype. Enceladus has a global, liquid, salty ocean. That ocean touches rock at its base. There is strong evidence of hydrothermal activity down there, the same process that fuels entire ecosystems on Earth's ocean floor. The ocean contains organic molecules, some of them complex, some of them fresh, actively being produced rather than sitting as ancient leftovers. It contains hydrogen cyanide, a foundational molecule for the chemistry that eventually builds amino acids. It contains phosphorus in abundant amounts, closing what was once considered the biggest missing piece. And now, thanks to the North Pole heat discovery, scientists have real evidence that this ocean is not just chemically promising. It is thermally stable, likely to remain liquid over geological timescales, rather than freezing over in some cosmic blink of an eye. That is an extraordinary list of ingredients. It is genuinely one of the strongest cases for potential habitability anywhere in the solar system outside of Earth itself. But it is still a list of ingredients, not a discovery of life. No instrument has ever detected a living cell, a metabolic process, or a biosignature that could only be explained by biology. Every single piece of this puzzle is consistent with life being possible there. None of it is proof that life exists. So naturally, the next question is obvious. When do we actually go back and check? Right now, there is no active spacecraft at Enceladus. Cassini deliberately burned up in Saturn's atmosphere in 2017, a planned ending designed to protect any potentially habitable moons from contamination by the spacecraft itself. Since then, everything scientists have learned has come from digging back through the data Cassini already collected, squeezing new insight out of old readings using better instruments, better models, and better computing power. That is genuinely remarkable, a spacecraft that has been dead for years, continuing to produce headline science almost every few months. But it also has limits. There's only so much a decade-old data set, collected by instruments never designed to detect life directly, can tell you. The real answer is expected to come from Europe. The European Space Agency is developing what it calls a flagship L4 mission, aimed specifically at Enceladus, with the explicit goal of searching for life rather than simply studying chemistry from a distance. As of 2026, the agency is finalizing the list of scientific instruments the mission will carry, with a special workshop planned for late this year to present results before an official call goes out for instrument development. According to the current plan, the mission would combine an orbiting spacecraft with a lander built to survive and operate on Enceladus' surface for at least 2 weeks, running on batteries and conserving energy carefully given how little sunlight reaches Saturn's system. That lander is expected to carry a mass spectrometer, a micro camera, meteorological and geophysical instruments, and, most importantly, a dedicated biomarker detection laboratory designed to search directly for signs of life rather than simply cataloging chemistry. But before anyone gets too excited about an imminent answer, it is worth being upfront about the timeline, because it is a long one. Formal approval of the mission is not expected until around 2034. Current plans point to a launch around 2042. And because of how far Saturn sits from the Sun and how long it takes to get there using realistic propulsion, the mission's landing on Enceladus is not projected to happen until around 2052, timed specifically for a period when Saturn will be in permanent sunlight, giving the mission's solar-dependent systems the best possible operating conditions. Teach Gaia. That means the generation of scientists who grew up hearing about salt, hydrogen, and phosphorus on Enceladus may be the same generation watching, decades from now, as a lander finally sets down on that ice and starts searching directly. It is a strange kind of patience that space science demands. The plumes were discovered in 2005. Phosphorus was confirmed in 2023. Hydrogen cyanide followed later that same year. Fresh organics were confirmed in 2025. The North Pole H heat balance was confirmed in July 2026. Each discovery on its own might not feel like a bombshell, but stacked together over 2 decades, they tell an unmistakable story of a moon that keeps saying yes every time scientists ask it a new, more specific question. That is really the heart of why this matters. Nobody flew a single mission that found life or changed everything in one dramatic afternoon, the way headlines love to suggest. Instead, one spacecraft, launched decades ago, kept handing scientists more and more reasons to take a small, icy, unremarkable-looking moon seriously, one careful measurement at a time. Salt, then hydrogen, then phosphorus, then hydrogen cyanide, then fresh organics, then a balanced heat budget suggesting the whole thing has been stable for a very long time. Each discovery narrowed the list of reasons Enceladus could not support life without ever actually proving that it does. And that is exactly why scientists keep calling it one of the best candidates in the entire solar system for finding life beyond Earth. Not Mars, with its cold, dry, radiation-blasted surface and a habitable past that may be billions of years gone. Not Europa, Jupiter's icy moon with its own hidden ocean, though it remains a serious contender in its own right. Enceladus offers something neither of those worlds can. A direct sample of ocean water sprayed into space for free, available to any spacecraft willing to fly through it and catch what comes out. It is worth sitting with that comparison for a moment because it explains why so many astrobiologists rank Enceladus above its more famous rivals. Mars almost certainly had liquid water once, billions of years ago, and might still hold pockets of it deep underground today, but any sign of ancient life would require digging through rock and soil to find it, a slow and expensive process, even for a rover as capable as Perseverance. Europa likely hides an ocean even larger than Enceladus's beneath its own icy shell, and it remains high on the priority list for future missions, including NASA's Europa Clipper. But Europa's plumes, if they exist at all, are faint, inconsistent, and hard to detect, and its ocean sits beneath a thicker, more complicated shell of ice. Enceladus, by comparison, is doing the sampling work for us. Its geysers fire hundreds of miles of ocean material directly into open space on a predictable, ongoing basis. which is precisely why Cassini was able to fly straight through them and catch fresh material without ever having to drill, land, or dig. So where does that leave things today, in the summer of 2026? The chemistry keeps checking out, the heat budget checks out, the organics keep getting fresher and more diverse every time someone looks closer. T. He mission that could finally answer the question directly is real, funded in its planning stages, and moving forward, even if its landing is still decades away. Nothing here has changed everything in a single moment. What has changed is something arguably more important. The scientific confidence that this is a question worth spending decades and billions of dollars chasing. That confidence did not exist 20 years ago. It exists now, built measurement by measurement, on data from a spacecraft that stopped transmitting nearly a decade ago and still has not finished telling scientists what it saw. Whatever happens next, one thing is already true. A small moon that used to be a footnote next to Saturn's rings is now one of the most closely watched objects in the entire solar system. And the case for taking it seriously did not come from speculation. It came from salt, hydrogen, phosphorus, organic molecules, and a heat budget that balances almost too perfectly to ignore. There's also something worth remembering about how this whole body of knowledge came together, because it says as much about the nature of scientific discovery as it does about the moon itself. Cassini launched in 1997, arrived at Saturn in 2004, and stopped transmitting in 2017. Every single finding described here, the salts, the hydrogen, the phosphorus, the hydrogen cyanide, the fresh organics, the CNOPS elements, the balanced heat budget, came from a fixed pool of data collected during those 13 years. No new spacecraft gathered any of it, no new probe falls. You threw a fresh plume. Scientists simply kept going back to the same archive, asking better questions, applying newer analytical techniques and running more sophisticated models. And the data kept giving up neat new answers every time. That is a quiet but important lesson. Sometimes the next big discovery does not require a new rocket at all. It just requires looking harder at what you already have. It also explains why coverage of Enceladus tends to arrive in bursts rather than as one single tidy announcement. A study on organics drops in late 2025. A reanalysis confirming CNOPS elements follows a few weeks later. A heat flow paper lands in the middle of 2026. Each one, taken alone, sounds like a modest technical result, the kind of headline that might not grab much attention outside of scientific circles. But viewed together, stacked chronologically over 20 years, they form a slow, steady, unmistakable pattern, one where every new answer makes the case for habitability slightly stronger and never meaningfully weaker. That pattern, more than any single press release, is what has convinced the scientific community that this small, ice-covered moon deserves a mission of its own. None of this means the answer is guaranteed. Chemistry that supports life is not the same as life itself, and there is a version of the future where a lander finally reaches Enceladus in the 2050s, drills into fresh material, runs every test available, and comes back with nothing. That possibility is real, and any honest account of this story has to leave room for it. But there's also a version of the future where that same lander finds something that cannot be explained by chemistry alone, a genuine biosignature, sealed inside ice that formed in an ocean humans have only ever sampled from hundreds of miles away. Either outcome would answer one of the oldest questions our species has ever asked, and either outcome starts with the same 20 years of patient, unglamorous, data-crunching work that built the case for Enceladus in the first place. For now, the moon keeps it secret. The ocean keeps churning beneath the ice, venting its geysers into space on schedule, indifferent to the decades of human argument over what might be swimming, or growing, or reacting somewhere in its depths. Scientists keep refining their instrument. TS. Engineers keep drafting mission plans decades ahead of launch. And somewhere in an archive at NASA, there is very likely more Cassini data waiting for someone to ask it the right question, the same way scientists did with salt, with hydrogen, with phosphorus, and with heat. That is the real headline, even if it does not fit neatly on a thumbnail. Not that everything has changed in a single moment, but that a small, icy, once-forgotten moon has spent 20 straight years answering every question scientists throw at it with some version of yes, and there is still no